All right. Hello, everyone, and welcome. So here, again, we'll start off with something relatively straightforward. I'm giving you a parallelogram ORTH with some information here, and our goal is to determine the numerical measures of all four angles. Okay. Well, again, give it some time, think about it here, and then we'll go over it a bit. Okay. So notice how in this situation here, right, we have this sort of thing about angle O and angle T. I'm not exactly sure about them here, but remembering how we label quadrilaterals here, ORTH, the nice part about this is that O and T are sort of separated from one another. So if we drew a parallelogram like this, for instance, right, and I picked, without loss of generality, I picked O down here. I could put R here or R here. So R could go in the upper left corner or in the bottom right corner here, right? But no matter how I do this, is because, remember, we label the vertices in the order in which we arrive at them by going around the perimeter of the quadrilateral. No matter how we do this, T is always going to be here. So it really doesn't matter which one we do here. So we have this. So we have in this situation here, this is 3z plus 15. This is 4z minus 10 here. So notice that now we see that these are opposite angles. And one of the first things that we remember is that opposite angles of parallelograms are congruent here. So I can say in this case, 3z plus 15 equals 4z minus 10. So it looks like we can subtract 4z from both sides. So let me go ahead and do that. We end up at negative z plus 15 equals negative 10. We can subtract 15 from both sides here. That goes away, and you're left with negative z equals negative 25, which implies that z is 25. That's great, because now we can actually fill in the rest of this here. Now that we know z is 25, we can go ahead and fill this in. So angle O here in this situation, angle O, this is 25 here, so we end up with 3 times 25 plus 15 here, and you end up with 75 plus 15, which is 90 here. So we have a 90-degree angle here. And then here we have 4z minus 10. This is 4 times 25 minus 15, which is 90 degrees as well. So that's a 90-degree angle as well. And now we can actually figure out the rest of this here, since that means these other two angles, they're both congruent. These two 90-degree angles take up 180 total, so it's 180 from 360. 360 is in the pool. We've used 180, so we need 180 left over. And that creates two 90-degree angles here. Okay, that seems pretty fair. Now note here, ladies and gentlemen, that for something like this looks a little bit strange. Obviously the picture doesn't look very good here. It doesn't look like it's drawn to scale. So let me go ahead and draw it more to scale here. And if you draw it more to scale, this should now look a lot more like a quadrilateral that we're all familiar with, which is probably one of the first quadrilaterals that you learn about. And you see that this here happens to be our rectangle. So note that our definition, our rectangle here, can actually be defined in very many ways here. And we'll actually talk a little bit more about the definition of a rectangle in a bit. But we can define a rectangle like this here. We're going to define a rectangle as so. We can say that a quadrilateral is a rectangle if and only if it's a parallelogram that contains a right angle here. Okay? If and only if it is a parallelogram that contains a right angle here. That seems pretty fair. Now, one may ask, wait a minute, don't we need 4 right angles? Well, let's try it out here. Maybe we can figure out what's going on here. If I got a parallelogram here, for instance, let's say this is a parallelogram. P, Q, R, S. And I say that this is a right angle. Notice that we can actually force every other angle to be a right angle. One of the things about parallelograms is that the opposite sides of a parallelogram, opposite angles are congruent. So that means angle R is forced to be a right angle like this. We also know that consecutive angles of a parallelogram are supplementary. Two angles that are neighboring each other have to sum to 180. This is 90. Angle P is neighboring to S, so that means S here is 180 minus 90, so that's also 90. But note that P is also neighboring to Q, so that's also 180 minus 90, which is 90 as well. So it turns out that one angle actually forces all 4 of them, so, which is why for the rectangle we only need one right angle. If we can show that we have one right angle here, that's enough to prove that this is a full quadrilateral here. Okay, so this is a rectangle here. So one of the nice parts about the rectangle like this here, right? We note that, the rectangle has specific properties. Now, in this situation, we can see that the rectangle here has all this. But the nice part about this is that if you look at the definition, it says parallelogram. So by law, we can say that one of the properties of the rectangle is that it has all the properties of the parallelogram, right? And I think we can see here that's pretty straightforward here, right? Something like that. Now, in addition, we also have just shown that for a rectangle, all the angles are right angles. That's also an important thing here, okay? And so, in a way, you can think of the rectangle as a specific type of parallelogram, right? We're going to be looking at this as a special parallelogram. This special parallelogram has these specific properties here. In this case, this property, one of the redeeming properties of the rectangle is that all the angles are right angles. And then finally, one of the things you can show is that the diagonals must be congruent to one another. So note that the diagonals being congruent to one another is actually not too hard to prove here, right? If you have a rectangle, you should be able to very easily show that all the right angles are right angle, all the diagonals must be congruent to one another, like this, right? We can just do a very quick proof sketch of this here. So in this situation here, one of the things about this is that, well, I want to show that zx and wy are congruent here. Well, it shouldn't be too hard to see. Wait a minute, I've got myself two overlapping triangles here. I've got this triangle like here, zwx, right? This triangle down here, and this triangle over here, yxw, right? Well, these aren't too hard to show that they're congruent, right? They both share wx, so that's pretty clear. They both have right angles, and right angles are congruent here because we know that's one of the properties of the rectangle. And we know ZW and XY are opposite sides of the parallelogram, so they're opposite sides of a rectangle. Now, note that in this situation, it shares the properties of the parallelogram, so you don't have to say it's a parallelogram first. It's part of the definition of the rectangle, or it's part of one of the properties of the rectangle. So you can say, if you're trying to cite this in a proof, you can say that instead of saying opposite sides of a parallelogram are congruent, you can say opposite sides of a rectangle are congruent, and that would be just fine here. And that gets you this. So it looks like I got side angle side here for congruence, and that guarantees you what you want there. So the rectangle seems to work out very nicely. As you can see, all the pieces seem to work out very well, and you should be in good shape with this here.